Hi, my name is Jamie DeYoung, and I created this video on the quotient rule for the course MAT135 at the University of Toronto. The goal of this video is to derive the quotient rule for finding the derivative of a quotient using first principles. So what do we mean by that? Well, if we have two functions, f and g, and we take the quotient f divided by g, the question is, what's the first derivative of the function q? And we're going to try and find that in terms of the functions f and g and potentially their derivatives. We want to find an expression for finding the derivative of q so that we don't have to do it function by function with the entire fraction involved. We could perhaps differentiate f, differentiate g, and use those to find the derivative of q. And we're going to do this using the definition of the derivative. So what does the definition say? Well, by definition, the derivative is the limit as h goes to 0 of q evaluated at x plus h minus q evaluated at x divided by h. And, well, we know something about what q is. It's f divided by g. So we can replace q in this equation with f divided by g, so we get the limit as h goes to 0 of f of x plus h divided by g of x plus h minus f of x divided by g of x, and this is still all divided by h. Now, our numerator actually has two terms now. We'd like to try and combine them into one so that we don't have a fraction of fractions. So our first term has a denominator of g of x plus h. Our second term has a denominator of g, so we'd like to write these fractions so that the denominator is g times g of x plus h. So that means we multiply the first one by g of x divided by g of x. And the second term we multiply by g of x plus h divided by g of x plus h. And that gives us the same denominator, so we can combine that in with the original denominator of h, and we just have one fraction as opposed to a fraction of fractions. What can we do from here? Well, you'll notice this f of x plus h that hopefully looks a little bit familiar. It seems related to finding the derivative of the function f, which might be easier than directly finding the derivative of q. But we would expect to see f of x plus h minus f of x. And unfortunately, the f of x term is actually multiplied by something different. It's multiplied by g of x plus h rather than by g of x. So if we want to bring in the first derivative there, we're going to have to essentially add and subtract that term so that we aren't adjusting what we already have. So we can do that. We have g of x, and it's multiplied by f of x plus h. And if we have the first derivative, we would expect this to have minus f of x. Now we still are subtracting f of x times g of x plus h. And we created a new term. We have this g of x multiplied by negative f of x. So we're going to have to account for that now by also adding it in. So now this line is equivalent to the first line, the previous line, sorry. So now let's look at these other terms. We have a g of x plus h and a g of x, and they are multiplied by the same term, f of x, and they do have opposite signs. So this actually looks a lot like the first derivative of g. So if we factor this, because we have f of x in both terms, we get minus f of x, and it's multiplied by g of x plus h minus g of x. So it kind of looks like we've just made things significantly more complicated, and we sort of have, but we have some more familiar looking terms now. We actually have something that looks kind of like the derivative of f and the derivative of g. So from this, we can apply our limit rules. So the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. So we can apply those rules. And what do we get? Well, in our first term of the sum, we had the limit of f of x plus h minus f of x divided by h. And this is multiplied by g of x divided by g of x times g of x plus h. So we'll just separate this out so that we have something that looks more distinctively like the derivative. And our other term, we have a g of x plus h minus g of x divided by h, and the remaining terms are an f of x in the numerator and a g of x times g of x plus h in the denominator. So this is just rewriting the line we just had, but making sure that things are separated a little. So this bit here looks like f prime, and this bit here kind of looks like g prime of x. We have to be careful and make sure that those are actually the limits we're taking. But we can apply our limit rules. And so we can take the limit of each of these pieces. So we get the limit as h goes to 0 of f of x plus h minus f of x divided by h times the limit as h goes to 0 of g of x divided by g of x plus h. And we can do the same with the other term. We have the limit as h goes to 0 of g of x plus h minus g of x divided by h times the limit of the rest of the product, which is f of x divided by g of x times g of x plus h. So we've split this up now into 4 different limits that are making up this expression. And what's left to do is to evaluate them. So this first one, the limit as h goes to 0 of f of x plus h minus f of x divided by h. That is, by definition, the first derivative of f of x. Now, the limit as h goes to 0 of g of x divided by g of x times g of x plus h. Well, the g of x's cancel, And we're left with g of x plus h, which as h goes to 0 tends towards g of x. So we get 1 over g of x. Now we have the limit as h goes to 0 of g of x plus h minus g of x divided by h. That is, again, by definition, the first derivative, but this time of g. And the other term in this product, we have as h goes to 0, f of x divided by g of x times g of x plus h. Now, once again, g of x plus h tends towards g of x. So this will give f of x divided by g of x squared. So now we don't have any limits anymore. We have two terms. It might be nice to try and combine this into one fraction. So let's do that. We have a g of x squared as the denominator on one term and g of x on the other term. So overall, we're expecting a denominator of g of x squared. So we'll multiply this first fraction by g divided by g. So we get f prime of x multiplied by g of x. And in the denominator, we'll have g of x squared. And for our other term, well, it was already dividing by g of x squared, so it stays exactly the same. We get g prime of x times f of x. So if we have our quotient, f divided by g, and would like to calculate the first derivative, then what we can do is calculate the first derivative of each f and g, and then we can compute the f prime of x times g of x minus g prime times f, and divide that by g squared. So we don't have to work with the quotient as a whole. We can simply calculate the derivative of the numerator and the denominator, and then we have a nice formula now for the derivative of the overall equation. So we'll be finishing there, but if you have any questions, feel free to come and talk to me, and hopefully you can use these techniques to find formulae for other general functions, as opposed to just differentiating specific functions by first principles, but actually taking something general and figuring out a simpler way to differentiate it. Thank you.